The next topic is thin-walled pressure vessels. So we're done now with axial stress, shear and bearing. The next is stress on a thin-walled pressure vessel. So a cylinder or spherical shell is considered to be thin when the wall thickness T is less than or equal to D over 20, where D is the internal diameter. So keep that in mind, capital D, internal diameter. Now, for the purpose of our lecture, every vessel that we'll encounter is thin. Okay, so we don't have to go through this criteria to check whether the vessel is thin or not, okay? And generally, cylinders are employed for transporting or storing fluids or liquids and gases. For example, LPG cylinders, boilers, and storage tanks. So it looks something like this. This is a cylindrical vessel, this is a spherical vessel, used to store or transport liquids or gases. Now, because of the presence of those substances, there will be a resulting pressure within this vessel. Okay, that pressure means there's also going to be force on your vessel as well. And of course, that force will also create stress on the walls of your spherical and cylindrical vessels. And that is what we'll talk about in this lecture, the stress, force, pressure on these types of vessels. So these are the equations summarized already. We have bursting, tangential, longitudinal stress. Now let's derive how these equations came to be. Let's start with force, specifically bursting force. Okay. So bursting force let's start with the sides of your cylinder, okay? So what do I mean sides? So let's focus on this cylinder, right? This cylinder will experience force along this area and this area. Let's start along this area, the sides. Okay, we call these the ends. We'll call this the sides. To analyze, let's cut isolate the same way we did for method of sections and for your axial stress and whatnot. So I'm gonna cut this lengthwise, okay? And then isolate either the top or bottom. I'm gonna isolate the top and then look at it from the front view. And that's gonna look like this, okay? So this is the length of your vessel. Okay, that's this one, the length. I just shortened it to fit the canvas. This is the length. And then this is the semi-perimeter. This is the entire vessel, okay? Now, to solve for the total force acting on your vessel, we'll just consider a differential area, okay? So differential area is a very small area, which I highlighted here. So this is your differential area. Let's call that your dA, okay? And this dA, since it's very small, it looks like a rectangle, right? The area of a rectangle is base times height. Base is this, which is the same as the length of your vessel. Height turns out to be this. So let's write SL. Now the problem is, what's that S? That S, if you look at the drawing, is the same as the arc length on the perimeter of your circle, right? If we draw that, this is the center, okay? I'm just maximizing it or magnifying it, okay? And then this was the resulting arc length forming the height of my differential area. Now, since that's a small area, differential area, we'll call the angle subtending that arc as d theta, okay? And then this is simply half the diameter, right, or radius of your circle. Now, can anybody tell me what is the equation for arc length again? The basic equation. Correct, Tristan. Very good. And Nicole Beltran. de los Reyes. Okay, good. R theta. Recall S equals R theta, right? Okay, let's write that. R theta. But in regards to this drawing, instead of R, let's write D over 2. Theta, instead of theta, that's D theta. L. Okay. So now I have an equation for area. Why is that important? Because that is where we'll base our equation on. Okay, so now let's figure out force. Okay, I want to get the total force, and force is distributed this way, all around. Now, if you look closely, you'll notice that the horizontal parts of the force all cancel out because this is a force to the left, force to the right. Everything has their partner on the opposite sign. So, let's write that out. Horizontal forces cancel out. So what does that mean? That means the total force is simply a vertical force F. Okay? And considering, let's say, this is what we're working on first, right? Let's get the vertical component of the force acting on this small area. So this is your F, okay? This is theta, angle from the horizontal. And this is what I need, the vertical component FV. And as you can see, we can just use trig functions to figure out what FV is. Using sine function, sine theta is simply opposite, which is your vertical force. In this case, that vertical force again corresponds to the total force all over hypotenuse, which is your F. So again, FV is simply F sine theta. Okay? And another thing, right? Another equation for F is that it's also equal to PA. Right? Pressure equals force over area. So force equals PA. So let's combine all of that equation, all of those equations. So force, okay, again, that's total force, would equal all of the vertical forces along this area, okay? So let's say summation of FV, right? And FV again has this equation, F sine theta. Sine theta, and once again, F is also equal to PA. So PA sine theta, and A has this summation of P, and then D over 2, D theta L sine theta. Now, remember, when we take the summation of differential elements, that's not summation anymore, that's integration, okay? So let's simplify all these equations into integral calculus. Okay, so that's all just integral of PA sine theta. Okay, PDA sine theta, right? This is your force sine theta. And then let's write dA, that's P, D over 2, D theta L sine theta. And now let's simplify this equation. To simplify, you have to figure out what are your constants. One constant is pressure. Pressure is the same in your vessel, no matter what portion of the vessel you're taking. So I can factor that out. So P. Diameter is also the same, right? Diameter of vessel doesn't change. Length of your vessel also doesn't change. So we're left with integral of sine theta, d theta. And then let's solve. P d over 2L. Now the question here is, this has to be a value, right? So this is an indefinite integral. I have to change that to a definite integral. To do that, you have to figure out the limits. Now to get that, just look at our figure, right? this is the portion that we isolated, half of your vessel. Now, if you plot that on your Cartesian plane, right, our area would span from this side going towards the other side. Again, if we try to draw that on a Cartesian plane, let's say this is the right side going towards the left, you're spanning from 0 to pi, right? That's the angle that we're spanning from this small angle of 0 to the total angle pi. Okay? So limit 0 to pi. 0, pi, 0, pi, 0 to pi. And then integral of sine theta is negative cosine theta. And now we just evaluate from 0 to pi. Okay? All right. So PD over 2L negative cosine pi. Cosine pi is negative 1 minus cosine 0. Cosine 0 is also negative 1. So you'll have PD over 2L, and this is just positive 2 minus positive 2 plus positive 1 plus 1. That's just 2. And as you can see, we can cancel something out. 2. Okay? PDL times 2. And then they'll cancel out 2. Finally, therefore, your bursting force F is just simply PDL. Okay? So that's our equation. Now, there's an easier way to solve for this. Okay, and instead of literally taking the area of your vessel, we'll just use a projected area. Okay, so cutting the same way, it's the same as this, but now I've turned it to its side. Okay, remember I mentioned force is this way. Turning it on its side, the bursting force is now this way, okay? So this is your bursting force. Instead of considering this area, right, the actual wall, we're using a projected area, which is this rectangle. And then we'll use the equation again. Force is simply pressure times area. So force is pressure. Now the projected area on this curved surface turns out to be a rectangle with base the same as the length of your vessel, and height is now equal to this part, which is the diameter of your vessel. So equation of area for a rectangle, base times height, so that's just L times D, or D times L. And that's the equation also for bursting force, specifically at the sides of your vessel, right? Now that's the sides. We've only considered these parts, okay? Of course, these ends also experience force. So we'll solve for that as well, okay? These portions. We'll call that ends. And then to draw, once more, previously I cut lengthwise, now cut crosswise. So previously I cut this way, isolating top part. Now I'll just cut this way, isolating either left or right. Okay? So let's do that. And cut that, and then we have this part. Now, considering this portion, pressure creates force on the ends. Let's call that FL, because that's also known as your longitudinal force. Okay? So we'll use this concept instead of this to figure out the equation, okay? Just to make things faster. So at the ends, this is the area considered. This is the area experiencing the stress. Okay, previously it's this, now it's this. And then using the equation F equals PA. Okay, PA. So F equals P. Okay, what's A? What's A again? What's the equation for A here? Can anyone give it? Okay, correct. Panganil. And then Greco. A circle. This is a circle. So area of a circle, pi over 4d squared. And what's d? The inner diameter. Okay, so let's specify that this is d. Okay? And so, subbing that here, pi over 4d squared. Let's rewrite that. F is simply p pi d squared all over 4. And then let's specify that as your longitudinal force. Okay, and that's it. That's it for the equations for forces. Do you have any questions? Please answer in the chat. No questions, great. Let's move on to stress. Okay, as mentioned earlier, these forces also create stress. Like before, let's start with the sides of your cylinder. And the stress along the sides of your cylinder has a name. We call that tangential stress. Okay. Now to solve tangential stress, we'll cut isolate once more, as you can see here. We already know there's a bursting force along this projected area. Now this is an equilibrium. That means there will be reaction forces, specifically along the material itself. So that means along the walls of your vessel. So it's over here. Another way to think about this is, remember, wherever you cut, there will be resulting internal loads. So same thing here. And I cut here, there is a resulting internal load, which we call T. And that P is your tensile resisting force or reaction load. Okay? And as you can see, there's two portions that were cut along the cylinder. So there's T there and T there. And then this T creates stress or results in the stress along these areas as well. So you have sigma T to denote stress along that part. Okay. So tangential stress from bursting force on the ends of your vessel. Okay, now let's compute. Again, this is an equilibrium, therefore I can use equilibrium equation. Summation of forces equals 0. Let's take T as the positive direction, so it's to the right. It's this way, so T, there's two of them, so 2T. F is opposite to that, so negative F equals 0. And then you can write 2T equals F. F, no problem. I know that F, it's this one, PDL. The problem is, what's this T? Again, T is from the stress on the material. Okay, so tangential stress has the same equation, force over area. Again, the force in this case is your T, so T over A. And then from this, we have an equation for T, which is just stress times area. So let's sub that here. Twice stress times area equals, again, F has the equation PDL. Okay, now let's figure out what that area is. So stress T, area, again, this is the area experiencing stress. Okay, and if you can see, that's a rectangle. So again, area is base times height. Now we have to figure out what's the base and height of this. Base of this rectangle is this, which is the length of your vessel. Height is simply the thickness of the wall, right? Again, this is the wall of your cylinder. So this height is just the thickness of that. So this is just L times T, okay? Again, that's a rectangle, so base times height equals PDL. Let's simplify. L cancels out. Okay? And now we can create an equation for tangential stress, which is PD and then divide both sides by 2 and t. So over 2t. And that's it. Okay, so that's for tangential stress. We're not done. That's just for the sides. Once again, we have to consider the ends. And we call that, or the resulting stress due to the force on the ends of a vessel, call that longitudinal stress. Longitudinal. Which makes sense, right? Because we call the force on the ends as longitudinal force. So the stress is longitudinal stress. Once again, cut isolating. We know there's a bursting force acting at this portion of your vessel, which will be resisted by the portion that we cut. This is the portion that we cut, right? And then there's going to be a resulting resisting load, internal load, T. Okay, everywhere there's going to be T. But I simplified it to a resulting vector T, okay? And so again, this T doesn't act on this space, okay? It actually acts here along the edges where you cut. I just drew it that way to show that it's the total resisting force. And then, of course, where you cut, that is where the stress is present as well. So we have sigma L to denote your longitudinal stress. So, like what we did earlier, let's use equilibrium equation. Let's consider this as the positive direction. So T, FL is opposite to that, so negative FL equals 0. So P equals FL. Again, we know FL. We had it earlier. The question is, what's T? Again, we take T using the concept that stress equals force over area. Stress along this, we call that sigma L. Again, longitudinal stress. And then force is this tension P over area. So P is simply sigma L A. And then now the question is, what's A? Again, A is the portion that's cut. Okay, so that's this blue shaded region. Can anybody tell me the equation of that? Correct, Marino, but there's an easier way to write that. Correct, Chloe. And that is the area of a ring, which earlier we know as pi over 4d squared, outer diameter, inner diameter squared, right? But usually for vessels, inner, outer not given. What's given is the thickness of the wall. So instead of that, the equation is pi dt. Okay? Pi d perimeter times thickness of your circle or ring. Okay? And this is T. Yan. Okay, now that we know that, let's sub that here. T is this sigma L A pi dt equals FL. Again, FL is P pi d squared over 4. P pi d squared over 4. Let's cancel things out. Pi d. Therefore, sigma L is simply P d squared all over 40. And there, that is the equation for longitudinal stress. And that completes all of our equations. Now, let's compare. Sigma T, sigma L looks the same, almost the same, right? The only thing is, sigma T is simply twice or sigma L, right? And if you can analyze, times 2, you get this. Now, because of that, we can conclude sigma T is critical or is more critical. Now, what does critical mean? It means gonna experience failure first. It's a critical point, the weakest link. So, another way to say it. Okay, so that means if we're looking for maximum load it can carry or minimum dimension it needs, we have to use tangential stress because this is the point where your object will fail first. So remember, we design according to the weakest member, which is created by tangential stress. Okay, that's it. That's all the equations. Do you have any questions so far before we move on to problem solving? Please answer in the chat. No questions, great. Let's start solving. Number 1. A cylindrical steel pressure vessel 400 millimeters in diameter with a wall thickness of 20 millimeters is subjected to an internal pressure of 4.5 meganewton per meter squared. Letter A, calculate tangential and longitudinal stress. Letter B, to what value may the internal pressure be increased if the stress in the steel is limited to 120 meganewton per meter squared? Okay, let's write the given. Cylindrical steel pressure vessel, 400 diameter, so I'll call that capital D, 400. We're also given thickness, 20, internal pressure, 4.5. Thickness, 20. Internal pressure, that also means the applied pressure, P, 4.5 meganewton per meter squared. I'll just write MPa because by now you should know meganewton per meter squared is just MPa. Part A, we're just looking for tangential and longitudinal stress. Okay, let's start with tangential. Sigma T, which has the equation PD over 2T. So it's a matter of direct substitution. P 4.5, D diameter 400, over 2, thickness 20. Please solve. What's the answer? Correct verse. Emmanuel. And who else? Cyrus, correct. It's 45. 45 MPa. Now, a trick here is usually if you didn't convert anything and you have consistent units, your resulting stress will have the same unit as your pressure. Pressure MPa, so stress MPa. I didn't convert anything, so that will follow. And then next, longitudinal. We know that as PD over 40, but we also know that's just your tangential stress over 2, right? So please solve. What's 45 over 2? Correct, Christine and Burse. Emmanuel Franco. Burse. 22.5. Now you can also just do this. You should get the same answer. Okay, that's part 1. Part 2, letter B. To what value may the internal pressure be increased if stress is 120? So stress is limited to 120. So we call that maximum stress or working stress, okay? Usually we just write sigma W, okay? Not wood, okay? W is not wood. In this case, W means working stress. And that is 120 MPa. We're looking for what maximum pressure can be used. Now, same thing as what we've been doing. When we're looking for maximum force, in this case, it's maximum pressure, we base it off of the given stresses. We're given working stress. It's only one stress, so we'll use that. Now, we have 2 equations for stress on a vessel, right? Longitudinal and tangential. But remember, in designing and figuring out maximum minimum values, we'll use the more critical equation. In this case, again, for thin cylindrical vessels, critical is tangential, okay? So use sigma T since critical. And that sigma T would be the value for working stress. So sigma T equals PD over 2T. Once again, working stress Just by definition, that means that's the stress that you'll work with. So I'll sub that into our tangential stress. 120 equals P, which is what we're looking for, diameter 400 over 2 times 20. From this, we solve what's pressure. Correct? Christine? Yes. Janelle. Espanyol. Franco. Ako ka na eh. Sino pa? Cavero, correct. Franco. M. The answer is 12. Right. Okay. So 120 P 400. 12. Unit, again, same. If it didn't convert anything, so that's MPa. Okay, that's it. That's number 1. Do you have any questions for number 1 so far? Please answer in the chat. No questions, great. Let's move on to number 2. I'll just do it on the same page. Number 2, the wall thickness of a 4-foot diameter spherical tank is 5/16 of an inch. Calculate the allowable internal pressure if the stress is limited to 8,000 psi. Okay, now we're working on spheres. Let's write the given. Wall thickness of 4-foot diameter. So diameter 4 feet. And then thickness was 5/16 of an inch. Right, okay. And then stress limited to 8,000 psi. That means, again, that's our working stress. Sigma W, 8,000. By the way, just to clarify, the normal stress, shear stress, bearing stress that we've had previously are also your working stresses. Okay, it just so happens that there's symbols for those, so that's why I use the symbols for the stresses respectively. Here, it's just sigma. So to differentiate, I just wrote sigma W so that you'll remember that's a working stress, not an applied stress. Okay. All right, so the difference of this problem is it's a sphere. What we have are cylinders. So what are we gonna do? Can we apply your equations for cylinders to this spherical tank? Well, let's check. We can try to draw and derive our own equation. So let's get a cylindrical tank. Okay, sure. Okay. Sphere. Let's draw a sphere and cut it in half. Okay. As you can see, that's a sphere, right? I'm gonna cut it here. So we'll have this. Okay. Perfect. And then this is the cut area. Okay. So for this cylindrical tank, there's still bursting force along its sides. Okay, so same thing as what we had earlier. This bursting force will be towards all the directions. Okay, so that way, that way, that way, that way. And as you've noticed, all the horizontal forces will cancel out. So the only bursting force left is vertical towards your object. So like this. Okay? And then, remember, wherever you cut, there will be reaction forces. In this case, your tensile resisting loads. So along the portion you cut. So you have that all over there. Okay? And then to summarize that, I'll just use one vector, and that's your total tensile resisting force. Right? And then we also know wherever you cut, there's going to be stress there. So there's stress, 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 etc. And then from this drawing, we can create your free body diagram. Summation of forces equals 0. Let's consider this as the positive direction. T minus F equals 0. P equals F. P, we'll take that from the concept stress equals force over area. Again, our force creating stress along this portion is T over area. T is stress area. Stress area equals F. Okay, F now comes from pressure. Okay, and F equals pressure times area. So PA. Now you might think, oh, cancel. No, that's different. This is area for stress. This is area for force. Okay, that's different. Now let's create equations for each area. This is for stress. And we know, again, for stress, it's along the portion you cut, which is this shaded region, which is a ring. And we already know equation for a ring is pi dt, area of a ring, equals P. Now how about this? Now remember, usually, instead of using the actual curved surface for bursting force, what we do is we project it on a flat surface. So this is the actual surface experiencing the force, right? We won't do that. We just want a projected stress. Okay? A projected area, which would be this part, right? And that happens to be the area or in the shape of a circle. So this area is the area of a circle, okay? So that's pi over 4 d squared. And now let's simplify. D pi cancels out. We have an equation for stress. P d over 4t, right? And would you look at that? That's the equation for longitudinal stress, right? So in conclusion, for a spherical tank, we have longitudinal stress only. There's no tangential. Okay? So you don't have to go through this. If you have a spherical tank, you can just know, oh, that stress is this, okay? Well, now let's solve. Stress limited to this, so I'll sub that there. 8,000 psi equals P, which is what we're looking for, right? Times D, diameter given for feet. Okay, that's in feet. This is pounds per square inch. So convert feet to inches, which is simply multiplying by 12, okay? So times 12 all over 4 times thickness. Thickness also given 5 over 16. From this, please solve what's P. Correct. Christian Janel, Bolido Denaga. It's 208.33 psi. Okay, unit, again, it's the same as your stress. Same thing, whatever your pressure unit is, it's the stress unit. So whatever your stress unit is, it's also the pressure. unless you converted the unit of either. So I did not, so it's still PSI. And that's it for number 2. Any questions for number 2? Please answer in the chat. No questions? Great. Let's have the last example for today. Number 3. A vertical cylindrical gasoline storage tank is 30 meters in diameter and is filled to a depth of 15 meters with gasoline whose specific gravity is 0.74. If the yield point of the shell plating is 250 megapascal and a safety factor of 2.5 is adequate, calculate the required wall thickness at the bottom of the tank. Okay, it's not as straightforward as the past problems. So let's write the given and try to draw this. Vertical cylindrical gasoline storage tank, 30 meters in diameter. So D, 30 meters, okay? And this is a vertical cylindrical gasoline storage tank. So if you draw that, it's gonna look like this, right? I'll simplify that. I'll just look at it front view. Looking at it front view, you just have a rectangle, okay? This is your storage front view. Diameter 30. So, okay, let's include that. This is your 30. Okay, well, actually, yeah. And this is the thickness. Yeah. Okay. Is filled to a depth of 15 meters with gasoline. So I'll call that H15. And then filled. So let's say this. Gasoline, oh, let's use gray. This is your gasoline. And it's filled to a depth of 15. Yeah. Okay. What else? Specific gravity of gasoline, 0.74. Okay. Specific gravity, that has a symbol of G sub S. And then we're also given yield point. And what is that? Safety factor 2.5. Yield point. What's yield point? Yield point is the maximum stress an object can handle before permanent deformation. Okay, so any stress before that point, your object will go back to its original shape, because of course stress causes deformation usually, but it goes back to original shape afterwards. If your stress crosses that point, the yield point, deformation is now permanent. It's not gonna go back to original shape. And usually, we want to design objects so that it doesn't, we want to make sure that we have our loads not create stress past that yield point, okay? So by that logic, that means that yield point will now be the maximum allowable stress. And the symbol for yield point is sigma sub y, because again, it's a maximum stress. So sigma y, which is also your maximum stress in this case, 250. Yeah, 250 MPa. Okay, so keep in mind the definition. And then we have a factor of safety, 2.5. Okay, I think that's it. So the question is thickness. What is the required wall thickness specifically at the bottom of the tank? Okay, so since there's something specified there, let's mark that out. We want to get wall thickness over here. Okay, here at the bottom. So that means, remember, basic equation for force is pressure times area. So that means I would most likely need the pressure at that point, okay? And then remember, our critical stress is tangential stress. So we need PD over 2T, Okay, I can get B, it's given. P, I still have to figure that out. That P is the one here. So let's start with figuring out what P is, okay? So to get P, recall the following equations. For fluids, pressure is simply rho GH. And then what is that specific gravity? Specific gravity is simply density of your liquid over density of water. Okay. I don't know density of gasoline. I just know specific gravity. But I can use that to get this and GH given. Okay. So let's start with figuring out density of gasoline. So using the equation for specific gravity, okay, GS equals sigma rho over rho W, GS given 0.74 equals rho. Density of water, this density of water, if you don't remember, it's 1,000 kilogram per meter cube, okay? And then therefore, density of gasoline is simply 740 kilogram per meter cube. Now I have density, I can use this equation, P equals rho GH. Okay, rho is 740. G is 9.81. Okay, this is kilogram per meter, 9.81 meter per second squared. That's gravity. So I need my height to be in meters as well, which it is. It's 15. Okay. Again, this H is the depth of depth of the point. It's at the bottom, so the depth is 15. All right, so 15. Now you can solve for this, get a value, blah, blah, blah. I won't. Actually, you can. Sige, solve for it. What's the answer? To make things easier. Correct, Gwyneth and Eric Ablao de Guzman. De Guzman. It's 10,000, 108,891. Now what about the unit? Okay, this is kilogram meter, meter second meter. The resulting unit is not megapascal. It's going to be Pascal because Pascal is Newton meter. Okay, so keep this in mind. All right, now I have pressure. I can start working on stress. Now to do that, recall, I'm given a factor of safety, which was not given before. Okay, so the reason for that is in actual, we don't want to design according to maximum allowable stress. Okay, we want to use an allowance for that, which is provided by your factor of safety. Okay, so once again, in practice, we're not designing according to maximum stress that your material can handle. We want an allowance to that. We want something less than that. And we call that your design stress, your working stress, which is a familiar term by now. And in the past, all of the maximum stresses were considered design stress, working stress already because there's no factor of safety given. All right, but now we do. So we have to consider that. Now in equation form, factor of safety is simply your sigma max, maximum stress over your working stress. Okay, therefore, working stress is simply sigma max over Fs. Okay, and remember that working stress is what will sub into our equation. And remember, use sigma T since critical. All right, so let's sub. Working stress is your tangential stress. Sigma W is sigma max over F, which is also equal to the equation for tangential stress, PD over 2T. Okay, sigma max, that's your yield point, 250. So 250 over factor of safety, 2.5 equals P, which is what we want. I don't know, which is what we have, 10,000. Now here's the problem. That's Pascal. This is megapascal. So I have to convert. Okay, so take note of this. 1 Pascal equals 1 times 10 raised to negative 6 megapascal. So to convert this to MPa, I'll just multiply this by 10 raised to negative 6. Okay? And then D, diameter 30 meters. Once again, that's meters. Our unit, Newton millimeter, right? MPa. So convert meters to millimeter, that's just times 1,000 or 10 raised to 3. And then all over 2, and T is what we want. Please solve. What's T then? Correct. Gwyneth Janelle de Guzman Bolido. Okay. That's 16.33. And then unit, again, we were following the MPa, Newton millimeter. So resulting unit for thickness is millimeter. And that's it. That's it for number 3. Do you have any questions? Please answer in the chat. No questions? Great. We'll end our meeting there. Next meeting on Thursday, we'll answer numbers 4, 5, and 6. And that's it. On Saturday, you'll have your quiz number 1. Coverage is only until shearing stress and bearing stress. So this thin-walled pressure vessel, not included anymore, okay? This is advanced topic. And then you're done with your seat work. For those who haven't answered your seat work, you have until this Saturday to answer it, okay? So that's already beyond soft deadline. So you'll only get a maximum of 70% on it, right? Do you have any questions, concerns, clarifications before I dismiss you? Coverage of exam is from introduction to stress, review, method of sections, joints, all up to shearing stress, bearing stress. So everything I've discussed so far except for thin-walled pressure vessel. Okay. Any other questions, clarifications, concern? No more? Sure? All right. Since you don't have any more questions, I'll see you on Thursday. You may go. Goodbye, class.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Welcome.
Bye po, ma'am.